In this video, we'll discuss the method of separation of variables for the problem listed below. So we have the partial differential equation du dt as a function of x and t, where x is the position and t is the time, equals beta, the second derivative of u with respect to x, as of x and t, where x is between 0 and L, t is greater than 0. And we have the boundary conditions, which are representing that the ends of the wire are at temperature 0 degrees. So u of 0t equals u of Lt equals 0. And the initial conditions, u of x0, so when time is 0, equals f of x when x is between 0 and L, where the initial temperature distribution is f of x. So let's work out this problem using this method called separation of variables. So let's assume that u of x and t, it's a function that can be written x of x, let's make the x little x, times t of t. So we have a function of x only times a function of t only. So the du dt is going to be x of x times t prime of t, because if we are differentiating with respect to t, then x of x is going to be considered a constant. Du dx, well, let's do first the first derivative. Du dx equals x prime of x t of t, and the second derivative of u with respect to x, it's x double prime of x times t of t. So if we replace this into equation 1, we get x of x times t prime of t equals beta times x double prime of x times t of t. So I'm going to rewrite this as a proportion, where at the numerator we'll put the derivative, so x double prime of x over x of x. And if we take a look at x double prime of x is going to be multiplied with t of t, right? With t of t. So then t of t is going to go down here. And there is also beta, so I'm going to put it here. And then x of x, which is at the denominator, is multiplied by t prime of t. So here I'm going to put t prime of t. So we wrote this equation, or this proportion, where this is a function of x only, this is a function of t only. So in order for them to be equal to each other, they must be equal with a constant. So I'm going to use this constant lambda. But just for to make my computations easier, I'm just going to put minus lambda. So now let's have this discussion. Let's have x double prime of x over x of x equals negative lambda, and find the solutions for x of x. And then we'll discuss the second part, the one with the t. So we are discussing this part now. So if we take a look at the equation that we wrote, this can be written x double prime of x equals negative lambda x of x, or I can just move all the terms on one side and describe a little bit the equation that we have, where we have a second order homogeneous ODE, right? Ordinary differential equation. So how do we solve it? Using characteristic equation, so r squared plus r squared plus lambda equals 0, which means r squared equals negative lambda, which means r1, 2 is plus minus square root of negative lambda. This is a very important equation, which is going to come up in our discussion. So I'm going to highlight it in purple, and I'm going to come back to it from time to time. So now let's have these cases. Case 1, lambda is less than 0. So if lambda is a negative number, this quantity is going to be positive. So R12 is equal to plus minus square root of negative lambda, and there are two real distinct solutions. What does that mean? It means x of x is going to be equal to C1 e to negative square root of negative lambda x plus C2 e to square root of negative lambda x. Right? This is chapter 4. But we also have some initial conditions. So if I go back here, these are going to give us initial conditions. Like what? Well, let me write them in red. So the initial conditions are going to be x of 0 times t of t equals x of L times t of t equals 0. So t of t cannot be 0 because then it's going to give us u equals 0. So that's a trivial solution. But we can have x of 0 equals x of L equals 0. So this is the boundary conditions that we are going to use here in our problem. So x of 0 equals x of L equals 0. So if we replace them in this equation, we get x of 0, it's actually C1 plus C2 and equals 0. X of L, it's C1 e to negative square root of negative lambda L plus C2 e to square root of negative lambda L equals 0. So from the first equation, C2 equals negative C1, and we introduce it into the second equation and see what happens. So we get C1 e to negative square root of negative lambda L minus C1 e to square root of negative lambda L equals 0. So we can factor out C1 e to square root of negative lambda L, and we get to negative. So we get e to 2 square root of negative lambda L minus 1 equals 0. So this quantity cannot be 0 because it's an exponential. This quantity is not 0 because the only time would be 0 if L is 0, which would be the length of the wire is 0. It wouldn't make any sense. Lambda is 0, but in our discussion we started talking about the lambda being less than 0, so it cannot be 0. So the only possibility that we have is C1 equals 0. That would mean C2 is also equal to 0. So x of x is going to be 0, which will make the trivial solution. Right, the u of x and t will be 0 as well. So now let's discuss case 2. Lambda equals 0. So that would mean R1 equals R2 equals 0. So then x of x will be C1 plus C2x. So let's not forget the initial conditions, x of 0 and x of L equals 0. So what would mean is C1 equals 0 and C1 plus C2L equals 0, which means C2 times L equals 0. So again, the only possibility that we have is C2 is 0. So C1 and C2 0 will mean again trivial solution. So let's get to the interesting part. Case 3, lambda is positive. Then R12 are going to be plus minus square root of negative lambda. But if lambda is positive, this quantity is going to be negative. So we'll get plus minus I square root of lambda. That means x of x is going to be C1 cosine of square root of lambda x plus C2 sine of square root of lambda x. So how important was to actually master chapter 4, right? So initial conditions again, x of 0 is 0, and x of L is 0 also. So this is going to give us C1 equals 0. And the second one would be C1, well, C1 is also 0, so it's C2 sine of square root of lambda L equals 0. Well, we have two possibilities. C2 equals 0, which is going to give us again trivial solution, or sine of square root of lambda L equals 0. Well, sine of x equals 0 means x equals 0, pi, 2 pi, 3 pi. So what does that mean? In our case, it means square root of lambda L is going to be equal to n pi, where n can be, well, in this equation we can have plus minus, right? But in this one, we can say n, it's an integer. Now, because square root of lambda is going to generate, when we calculate it, we should get positive numbers on the left side, so the right side should be positive as well. So this is why we're going to say n is equal to 1, 2, 3, and so on. We are not writing n equals 0 because that would mean lambda is 0, and we don't have lambda 0. Our case is lambda is greater than 0. So this means square root of lambda equals n pi over L, L, which means lambda equals n squared pi squared over L squared, with n being 1, 2, 3, and so on. This lambda that we found finally, that is not going to give us trivial solutions, this is called eigenvalue. For these values, we actually have solutions. So x of x is going to be equal to, taking a look at x of x from here where we started, well, c1 was 0, so it's actually c2 sine of n pi over L x. So I'm trying to write it here. Well, n equals 1, 2, 3, and so on. But these are generating for every single n, we're generating a solution. So these c's are also changing, right? They are different constants. So we're going to say that x of x, it's actually sum, as n goes from 1 to infinity, of c sub n sine of n pi over Lx. So now let's take a look at what happens with the second equation, t prime of t over t of t equals, well, beta t of t equals negative lambda. So this one is giving us t prime of t over t of t equals negative beta. Well, we already found lambda, so n squared pi squared over L squared. This one is a simple problem where we just integrate. So we actually get ln of absolute value of t equals negative beta n squared pi squared over L squared t. So t equals a constant, let's call it a d, e to negative beta n squared pi squared over L squared t. So basically u of x and t is going to be the product of these two, as we started, right? So it's x of x times t of t. So it's actually sum, as n goes from 1 to infinity. I have a constant and then constant again, so I'm just going to write c sub n sine of n pi over Lx e to negative beta n squared pi squared over L squared t. And this is the solution to the heat equation. Now, given an initial, we had actually an initial condition, which I wrote here really quickly, u of x and 0 equals f of x, which means if we replace t with 0 here, we are going to end up with this equation. If f of x is given, and if f of x is actually a sine of x function, then we will be able to find this c sub n. I hope this helps.